Hello guys, I'm back with another video, and this is the most recent Unit 4 paper from just this January, the day before my birthday, coincidentally. All right, January 2026. Okay, and this is Unit 4. From what I saw, I don't know if this is a new trend or a new idea of from Edexcel, but they actually publish a Unit 4 and then a Unit 4A. And from what I saw, Unit 4A is different from this one. If anybody knows why, let me know in the comments. The plan is to solve 4A as well, and then we will go over Unit 5 and Unit 6. And as you guys know, I also started working with the UK Edexcel papers 1 and 2 so far, and I will do 3 at some point. So anyway, let's dive in. So section A, again, 10 questions, multiple choice, 1 mark each. It should take you about a minute to solve, okay? So let's start with 1. Which row of the table gives the number of neutrons and the number of protons in a nucleus of gadolinium 150? So pretty much the first and second columns have to sum to 150 pretty much, okay? Because this is Z and this is N. And then Z plus N gives us the mass number. So A and B are obviously wrong, and then we only C adds to 150. 64 plus 86 is 150, which is the mass number. All right? Now, question 2. Which of the following is a scalar quantity? By definition, the electric potential is a scalar quantity. Okay, impulse and magnetic flux density are vector quantities, and the same goes for electric fields. All right. Question 3. Which of the following is a reason why high energy electrons are used to study the structure of nucleons? A is to ionize the nucleons. This makes no sense. B, to produce individual quarks. That cannot happen, actually. You can never have individual quarks, okay? I forgot what it's called. It's been a while. Confinement is called confinement of quarks. Quarks can never be on their own. They need to come in pairs, okay? C is to allow elastic collisions. Okay, it's not it's not something important. And then D, to provide energy to produce new particles, which is the answer, right? Because if they have high energy energies, they can create new particles, and this is because energy and mass are equivalent according to Einstein's E equals mc squared. All right, 4. A wire carries a current of 0.12 amps. The wire is placed in a uniform magnetic field of flux density 0.075 teslas. The angle between the wire and the direction of the magnetic field is 40 degrees as shown. The length of the wire in the field is 4.6 centimeters. Which of the following expressions gives the force in newtons on the wire? All right, so pretty much the way I work these problems out is to take the current and analyze it into a horizontal component and a vertical component. The vertical component cuts through the magnetic field, so 0.12 times sine of 40 is the component that cuts through the magnetic field, whereas the other component, which is 0.12 cos 40 degrees, is parallel to the magnetic field. Therefore, it doesn't do anything. It doesn't create a force or anything. So F is BIL times sine 40 degrees in this setup, right? So you just have to read the answer. So A, B, and D are wrong pretty much. So C is the correct answer, okay? And it's the correct answer. You can kind of figure it out even by just analyzing the components, but it also works out if you substitute the expressions given. All right, I hope this makes sense. Let's move on to 5. 2 protons are 20 centimeters apart in a vacuum. Point X is 10 centimeters from one of the protons as shown. Which of the following expressions gives the electric field strength in newtons per coulombs at point X? Okay, so I'm going to show you the solution, but I'm going to show you a trick as well. Actually, let's start with the trick. Okay, A cannot be correct because these are positive charges. So you have to add two distances, okay? So A is wrong. B is also wrong because remember that the electric field is proportional to 1 over r squared, right? And then C is wrong because we are subtracting things. So D is the correct answer, but I can also show you the answer. So let's work it out. So we have two protons, right? So the electric field at X is K, and then E, which is the charge of one proton, over 0.3 squared, which is the distance of X from this one, from the first proton. So this is 0.3. And then plus the same thing, Ke over 0.1 squared, which you can immediately recognize as this option. Okay, so let's move on. Question 6. A vacuum tube is a type of diode. A metal plate in the vacuum tube is heated to release electrons as shown. So this is the thermionic emission of electrons, right? So a potential difference is applied between the metal plate and the electrode. Okay, so they mean here. Okay, so they put a battery there pretty much, okay, or a potential difference. Okay, I'm going to erase this now. Okay, where was I? Electrons are accelerated towards the electrode, and there is a current I between the metal plate and the electrode. So here, there is a current in this direction. All right, so the question is, which of the following changes would increase the current? So A, reverse the potential difference applied to the heater. It wouldn't matter because it could still heat it. So with this setup, current in the heater, by the way, never confuse this potential difference that hits the filament and this potential difference that accelerates electrons once they are emitted from the filament, okay? So if we reverse the current, nothing is going to change, okay? Then increase the potential difference applied to the heater. Okay, this is promising because if we increase the potential difference, we will increase the current, which will heat the filament more than before, right? So more electrons will be emitted. So this is actually the correct answer, but let's read the other ones. C, reverse the potential difference between the metal plate and the electrode. This will stop them, okay, because you will have a negative charge here, so the electrons will see it and get repelled, so there will be no current. And D, decrease the potential difference between the metal plate and the electrode. That will decrease the current. So, yeah. Let's move on. In the early 20th century, scientists, this is question 7, investigated the structure of the atom by directing alpha particles at thin gold foils. Which of the following is not a conclusion from the observations made during these investigations? Okay, A, most of the atom is empty space. That was a conclusion they reached, actually. B, most of the mass of the atom is in the nucleus. Okay, that's actually what they concluded. There is a concentration of charge in the nucleus, which is what they concluded. And then D, the nucleus consists of protons and neutrons. So that's the correct answer. Whenever you see neutrons in Rutherford, that's wrong, okay? Because Rutherford did these experiments. If correct me if I'm wrong in the comments, but I think it was 1915, and the neutron was not discovered until 1932, I believe. Please check my facts. If I'm wrong, let me know in the comments. But yeah, neutrons were not discovered by Rutherford. Okay, came much later. Let's move on. Question 8. A line arc accelerates charged particles to high speeds. The charged particles move in a straight line along a series of tubes called drift tubes. An alternating potential difference PD of constant frequency is applied between the drift tubes. Which of the following is correct? A, each drift tube is the same length. This is totally wrong because, as you know, the tubes get increasingly longer, okay, progressively longer, I'm sorry. B, there is an electric field inside each drift tube. No, it's outside, right? Because the potential difference applied on the outside of the tube. So no. C, the particles do not accelerate when they are inside the drift tubes. Okay, that's correct actually, right? Because they accelerate when they get outside, where the potential difference is. So C seems to me to be the correct answer. Let's read D. The applied potential difference changes polarity when particles are between the drift tubes. No, this happens when they exit. Okay, because, and again, I mean, you have drift tubes, something like this. Okay, so the potential difference applied here actually. Okay, so once they exit, they get accelerated, and the polarity changes when they exit. So no. All right. 9. An alpha particle and a proton enter a region. It sounds like a joke. A neutron and an electron enter a bar. Actually, there is this really lame joke. A neutron enters a bar and orders a drink, and then the neutron asks how much, and the barman says, "For you, no charge," which is totally stupid. Anyway, so an alpha particle and a proton enter a region of uniform magnetic field. The particles are deflected into circular paths. The alpha particle and the proton have the same initial velocity. Okay, that's the key here. Okay, same initial velocity. Which of the following is equal to the ratio radius of path of alpha particle and over radius of path of proton? Okay, so for circular motion, we need the total of all forces to be equal to mv squared over the radius, right? And here the force is qvb because it's a magnetic field. So qvb is mv squared over r. Okay, so the velocity cancels. So r, the radius, is equal to mv over qb. Okay, so the radius of the alpha particle is then alpha particle is, say, 4 times the mass of the proton times v over the charge is 2e, and then times b, and then the radius for the proton would be mass of the proton times v, since the velocity is the same, over eb, because the charge is just 1, right? So if we divide these two, okay, let's divide. Let's use a different color. So we divide, and if we divide, velocity cancels, b cancels, mp cancels, e cancels, and we are left with ra over rp equal to 4 over 2, which is 2. So the answer is C. Okay. Hope this makes sense. Again, please ask in the comments if something doesn't make sense. Then question 10. A ball of mass m is attached to a string. The ball is made to move in a vertical circle as shown. The ball moves in a circle of radius r. Its speed at the bottom of the circle is v. There is a tension in the string. Okay, which of the following expressions gives the tension in the string when the ball is at the bottom of the circle? Okay, so let's do a free body diagram. So we have the weight. Oops. Okay, and it should be vertical. Okay. Too much technology. Okay. mg. The weight is down. The tension is up. This thing undergoes circular motion. I used to make toys like that. I used to tie a rock at the end of the string, and I was rotating and throwing it. Thankfully, it didn't hit anyone because it could be dangerous. It was actually dangerous, but I was a kid. So anyway, tension minus mg, right? Since we have circular motion, the sum of all forces has to point inwards, right? So we have tension as the positive one. So T minus mg is equal to mv squared over r. And T is mg plus mv squared over r. This is option D. All right. Okay, this was part section A. We are now ready for section B. Again, for those of you who have been watching my videos, they probably heard this a billion times by now, but for those of you who are new, I tell my students that in this type of test, it's good to spend as much time on a problem as the marks are awarded for the problem. So this is a 2 marks problem, for example. So you should spend about 2 minutes. You shouldn't be religious about it, but it's a good rule of thumb. Okay, maybe it will take you 3 minutes or 4 minutes, and then another problem that awards 5 marks might take you a minute, for example. Okay, so don't freak out about it, but it's general to keep track of time with these tests, so you don't run out of time and you have enough time to go over all the problems. I had a student who was really smart, but he was having trouble timing himself, so he lost lots of marks just because he ran out of time. So I don't want anyone to go through that. So question 11. An alpha particle is moving at right angles to a uniform magnetic field in a vacuum. Okay, calculate the magnetic flux density of the uniform magnetic field. So the situation is, let me use a clean page to draw it. So, okay, this is a circle, this is the middle, and this is the alpha particle, I guess. This is the velocity. The velocity is tangent to the radius. And by the description, the magnetic field is into the page pretty much. How do I know this? Because if we use Fleming's, you don't have to go through this, by the way, I'm just explaining. So Fleming's left hand rule, B is our index finger, so it should point in. Then V is our middle finger, so we have to make our middle finger point up, and F will then point, so our thumb is F, so F points inwards, therefore we have circular motion, okay? And what is the force that keeps this under circular motion? QVB, right? So sum of all forces is mv squared over r, so QVB is mv squared over r, okay? So yeah, this is the story. But in this case, they actually give us the force on the alpha particle, so it's kind of easier. So F is QVB, so we need to calculate B, which is F over QV, which is, and they also give us the speed. So I'm just gonna substitute, oops. Okay, this is a straight line. So the force is 9.2 times 10 to the negative 14. And then Q is 2 times 1.6 times 10 to the negative 19. And then V is 1.2 times 10 to the 7. And then, oops, what did I do? 10 to the 7. And then, okay, this is newtons. And this is coulombs, and then meters per second. Okay, and let me see, how does this work now? Okay, since it's new, okay, we know that this works out to Teslas, but I want to prove it to you. So anyway, let's move on. So 0.024, and this is Teslas. And the reason why it's Teslas is because we know that if we use F equals to QVB, then we know that newtons are equal to coulombs times meters per second times Teslas. Okay, so Teslas are equal to newtons times seconds over coulombs times meters, okay? Which is what we have over there. That's why I was able to substitute into Teslas, okay? So that's the proof. Now, let's move on to question 12. A carousel is a popular theme park ride. The riders sit on model horses as shown. I haven't done this since 1653 AD. I'm kidding, like it was a long time ago. So the carousel rotates and the riders move in a horizontal circle. The carousel takes 15 seconds to complete one revolution. Show that the angular velocity of the carousel is about 0.4 radians per second. So omega is 2 pi over the period. So 2 times 3.14 radians over 15 seconds. And if you have a calculator, you will see that this is 0.42 radians per second, which is 0.4 radians per second. Now, question B. The carousel is rotating. Two riders are at positions Y and X on the carousel. As the carousel rotates, the rider at X passes directly in front of the fixed point P. So this guy moves through P. The direction of rotation is this one. Okay, the rider at Y passes the fixed point P at a short time later. So Y has to go through all this rotation pretty much, okay? So you can see that, you can immediately see that delta phi, the change in angle, is going to be 360 minus 110, right? And why? Because it's this part of the circle pretty much. Their difference, you can see it, that the difference is this angle, right? So the whole thing is 360, so you have to subtract 110. So this is 250 degrees. Okay, so recall that omega is defined as delta phi over delta t. So delta t is delta phi over omega. So delta phi is 250, and then we have to multiply times pi over 180 degrees, because pi is 180 degrees, and then we have degrees in the numerator and degrees in the denominator, so they cancel out. And then omega is simply what we calculated earlier, which is 0.42. And here we have radians due to pi, and then we have radians per second. Radians cancel. And if you carry the calculation, you will find 10.38 seconds, which is about 10.4 seconds. Okay. Let's move on to question 13. In the upper atmosphere, high-energy cosmic rays interact with nuclei to produce pions. The pions decay into muons. Muons are leptons. Pions are mesons. State one difference between the structure of leptons and the structure of mesons. So mesons consist of a quark and an antiquark, whereas leptons are fundamental, meaning that you cannot break them into smaller particles. At least for now, I mean, with the physics we know now. Maybe in 100 years they will be splitting the, I don't know, the electron, we'll see. You guys are younger, so maybe you will experience some breakthroughs and crazy changes in physics in your lifetime. I don't know. In my lifetime, I'm not sure, but we'll see. Actually, in my lifetime, they discovered gravitational waves, which was something I didn't expect, to be honest. I mean, it's not that I doubted that they existed, but I was like, okay, this is too crazy and too delicate of a measurement to make, but they made it. So go read about gravitational waves. There is this experiment called, what is it? LIGO. Okay, it's really interesting, guys. I mean, for those of you who are interested in physics. All right, B. Muons are unstable particles. The particle equation shows a muon decaying into an electron, a muon neutrino, and an electron antineutrino. Deduce whether the conservation of charge and the conservation of lepton number apply to this decay. Okay, so let's start with charge. We have -1, right? When I say -1, I mean E, like the charge of one electron. So we have a charge of -1 and we go to a charge of -1. The neutrinos do not have charge, okay? So that's okay. And then the lepton number of a muon, the lepton number of a muon is 1. The lepton number of an electron is 1. The lepton number of a muon neutrino is also 1. And the lepton number of an electron antineutrino is -1, okay? So lepton number is also conserved, and we are ready to move on. 14, a student investigated the collision of two spheres. The diagram shows the spheres before and after the collision. After the collision, the spheres move apart at an angle phi. Describe how the angle phi can be determined experimentally. So let me demonstrate if I can. So you will use your cell phone, I guess, okay? It is not good only for selfies, guys. Okay, you can also use it to do physics. So you can take your phone. I'm not kidding. Open the camera and put it vertically on top, like I show. So the cameras are usually here. Okay, it's gonna be flipped. Okay, I guess. So you will film it from the top, pretty much. Okay, so it covers this arrangement. So use a video recording. Use a video recording device. Okay, play the video. Actually, record the video first, right? Record the collision. Stop the video. Use a protractor and measure phi. And that's the answer. So, and as I said, if you use a cell phone, put it vertically on top. All right. B. The student rolled a sphere of mass 51 grams with a velocity u into a stationary sphere of mass 32 grams. After the collision, the spheres began to move apart as shown. The collision was elastic. Okay. Show that u is about 0.25 meters per second. Okay, so I'm gonna come. So the situation is that you have your 51 grams. Okay, so 51 grams, and it moves with velocity u. Okay, so after the collision, you have the component of this velocity. Okay, which we will draw here. Okay, so that's 0.23 cosine theta. And then you have another component from this velocity, which is, let's draw it over here. Something like that, 0.17 cosine of 34 degrees. And then you will have another component that points up. It's not vertical for some reason. Okay, that one. So 0.23 sine theta. And then another one that points down, which is 0.17 sine of 34 degrees. Okay, I didn't follow the mark scheme because I actually didn't follow this. What am I? I'm trying to say that it's because you don't know theta. The way I worked this problem out was to actually calculate theta first and then find u. Okay, so let's do that. So in the horizontal, we have conservation of momentum. So 51 grams times U should be equal to 0.23 cosine theta plus 0. Oops, I forgot to multiply with the mass. So 32 is the mass of the second sphere times 0.23 times cosine theta, and then we have to add the second component, the second velocity, the horizontal component of the second velocity, which is 51 times 0.17 times cosine of 34 degrees. Okay, and then vertically we have 0.23 sine theta times the mass, which is 32, is equal to 51 grams, which is the second mass, times 0.17 times sine of 34 degrees. So sine theta is equal to 51 times 0.17 times sine of 34 degrees over 32 times 0.23. Okay, so theta becomes 41.2 degrees. Okay, so in part 2 they say the student determined that theta was 43 degrees. Deduce whether the student was correct. So student was correct, I guess, as theta is 41.2 degrees, which is okay, close to 43 degrees, but not absolutely 43 degrees. But okay, she would use a protractor, so that introduces errors and so on, so it's good enough. All right, and we are left with U. We haven't calculated U. Now that we know theta, we can go up here, okay, and calculate U. So we have 51 times U is equal to 32 times 0.23 times cosine of 41.2 plus 51 plus 0.17 times cosine of 34 degrees. So U is 0.25 meters per second. Okay, let me check the mark scheme really quick, because when I was solving it, I actually didn't use the mark scheme at all. So yeah, okay, yeah, that works. This is what they found as well. So let's move on. 15. Defibrillators save lives by delivering energy to restart a heart that has stopped. A defibrillator includes a capacitor and a pair of metal electrodes. The capacitor is charged by connecting it to a large potential difference. The electrodes are connected across the chest of the person, and the capacitor discharges. That sounds terrifying. A switch is used to charge or discharge the capacitor as shown. Okay. To charge the capacitor, the switch is connected to A. So here. Okay. All right. The question is, to restart the heart, the energy stored in the capacitor needs to be at least 150 joules. Deduce whether this circuit will provide enough energy to restart the heart. Okay, so the energy stored in a capacitor is 1/2 CV squared, since we know the potential and the potential difference and the capacitance. So 1/2 times 120 times 10 to the negative 6 times 1750 squared yields 183.75 joules, which is about 184 joules, which is larger than 150 joules. So there is enough energy. Okay. B. The electrodes are held on the person's chest by insulated handles. The switch is moved to position B The capacitor is then partially discharged across the person's chest. The initial discharge current is 20 amps. The discharge is stopped when the discharge current is 8 amps. Chest resistance of person is 87.5 ohms. Calculate the time taken for the current to decrease to 8 amps. Okay, first of all, let's find the time constant, which is equal to RC for this circuit. And the circuit includes the person. It's kind of scary. So the capacitance of the person is 87.5 times the capacitance, which is 120 times 10 to the negative 6, yields 10.5 milliseconds. Okay, now for both charging and discharging, the current follows I equals I naught e to the minus t over tau. So e to the t over tau is I naught over I, which means that t is tau and then ln of I naught over I, if we take the ln of both sides, that is. And if we plug in numbers, we find 10.5 times ln of 20 over 8 milliseconds, and this is 9.62 milliseconds. That's the answer. Okay. 2. Determine the charge on the capacitor when the discharge is stopped. Okay, this one gave me a little bit of trouble for whatever reason. Maybe I was tired earlier. So first of all, we have to find the initial charge. How do we find that? C is Q naught over V. So Q naught is C times V. So 120 times 10 to the negative 6 times 1750 gives 0.21 coulombs, which is the initial charge. And then we just apply Q is Q naught, and we know that this is the correct formula because it's discharging. Okay, so Q is Q naught e to the minus t over tau, so 0.21 e to the minus what is it, 9.62 is the time we found earlier, 9.62 over the time constant, which is 10.5, which we also found earlier. And if you do this, you will find 0.084 coulombs is the remaining charge. Okay. C. The capacitor must be recharged before the defibrillator can be used again. During the charging process, the charge Q on the capacitor varies with time t as this formula, okay, where Q naught is the charge on the capacitor when it is fully charged. Okay, the graph shows how Q varies with t as the capacitor is being charged. Okay, determine the resistance of resistor R in the charging circuit. Okay, so we will take Q naught. We can take it from the graph, but let's take it from what we calculated earlier, which is 0.21 coulombs. Okay, so since Q is Q naught times 1 minus e to the minus t over tau, then if t is equal to tau, then Q is Q naught times 1 minus e to the minus 1, pretty much. So, which means that Q is 0.63 Q naught. Okay, which means that Q is 0.13 coulombs. And then we go to the graph and we find where 0.13 coulombs is, which is that point over there, okay, which calculates to 45 seconds. It doesn't calculate, I mean, it corresponds. I'm sorry, wrong English, forgive me. So I hope you're following what I'm doing. So for a time equal to the time constant, Q is equal to 0.13 coulombs, okay? And then we come here and we find where 0.13 coulombs is, okay? Which is this point over there, okay? And this point pretty much corresponds to the time constant. So the time constant is 45. You can check for yourselves. So if Q is 0.13 coulombs, then T, which is equal to tau, is equal to 45 seconds, okay? So this means that R times C is 45 seconds. So R is 45 over C. We know what C is from before, 120 microfarads. And if we do the calculation, we find 3.75 times. Actually, I found, 3.75 times 10 to the 5 ohms, which is about 3.8 times 10 to the 5 ohms. And that's the answer. And there is a range in the mark scheme. I mean, I think there must be a range. Let me see. 3.8 to 4.6 times 10 to the 5 ohms. I mean, if you don't find this and you find 4 times 10 to the 5, it's good enough, okay? And now we are moving on to question 16. When a high-energy photon passes through a strong electric field, pair production can occur. In pair production, the high-energy photon creates a particle-antiparticle pair. An example of pair production is given by the equation, and we see the equation, where a photon creates an electron-positron pair. State two differences between an electron and a positron. So the electron has a charge of -1 and a lepton number of 1, whereas the positron has a charge of +1 and a lepton number of -1. Okay, so two differences. Right, B. A high-energy photon has an energy of 1.2 MeVs. Deduce whether the photon has sufficient energy to create an electron-positron pair. Okay, so we will use delta E is equal to delta mc squared, right? So this is what we will use. So in our case, we need the energy of the photon to have at least the energy of what the mass of 2 electrons correspond to, so 2mec squared. In other words, since mass is energy, 2 times the mass of the electron times c squared has to be equal to the energy of the photon. Okay, so let's plug in numbers. So 2 times 9.11 times 10 to the negative 31 times 3 times 10 to the 8 square. And then we have kilograms meter squared over second squared, and this corresponds to joules. Okay, so this yields 1.64 times 10 to the negative 13 joules. And if we divide 1.64 times 10 to the negative 13 joules by 1.6 times 10 to the negative 19 joules per electron volt, we find 102 times 10 to the 6 electron volts, which is equal to 102 MeVs, which is less than 1.2 MeVs. So this photon works. Okay. So C is a long writing problem, 6 marks. Okay, so in writing problems, again, those of you who have been watching these videos are familiar with this because I mention it probably in every video. So in writing problems, if the problem is 6 awards 6 marks, you have to provide at least 5, maybe 6, maybe 7 talking points, like writing points, different concepts or ideas. Okay, so let's start. Let's read the question first. So the tracks shown were produced by particles in a particle detector. There was a uniform magnetic field perpendicular to the plane containing the tracks. Explain how these tracks could provide evidence for a photon creating a particle-antiparticle pair. So the photon is not charged, so it doesn't leave tracks. Okay, so that's the first evidence. The electron-positron pair leaves tracks because they are charged. Because they are charged. Okay, and the tracks curve in opposite directions, which is an evidence of pair production. Okay, this means they have opposite charge. Okay, the radius of curvature is the same. So they have the same mass. Okay, and then since mv squared over r is equal to qvb, we will have already used this, so I'm not going to prove it. So which means that r is p over qb and mv is equal to p, right? And p, since the radius of the curvature is that, and since p is the same due to okay, this means the charge is the same. All right. 17. A teacher showed a simple alternating current generator to her class. The generator consists of a coil and a magnetic field. The handle is used to rotate the coil. The teacher connected a voltage sensor to a pair of slip rings as shown. Okay, we have the magnet, the handle, and the coil. The voltage sensor was connected to a data logger. Initially, the plane of the coil was horizontal and parallel to the magnetic field. The teacher rotated the handle at constant speed. Sketch a graph of mth electromotive force, okay, against time for 2 complete rotations of the handle as shown on the data logger. Okay, so we start with maximum mth, right? I'm going to explain in a moment why. So we start there, and we will have something. Oops, this does not look like a curve. So maybe this, okay. Okay, so 2 periods, so that's 1 period and that's another period. Okay, so the reason why mth is max at t equals 0 because we start with 0 flux, right? Because as you can see here, I'm drawing the magnetic field points this way, and the coil is parallel to the magnetic field, so it doesn't cut through the lines. And then immediately when the teacher starts turning that, we go to a maximum exposure, like we the coil immediately cuts through the line, so we have a maximum length. Okay, so let's write that down. Immediately after the teacher rotates the coil, phi, the flux, becomes max. So the electromotive force is max at t equals 0. Okay. Yeah, let's move on. 2, the teacher doubled the speed of rotation of the coil. Explain how this affected the graph shown on the data log here. Okay, we're not gonna, maybe we can go back and draw it, but let me explain a few things. So the magnetic flux is B times A times sine omega t, which you can also write as BA sine 2 pi t over the period. How do I know this? Because at time equal to 0, we have 0 flux, right? So if we substitute t equal to 0 there, we have 0 flux. And if we substitute t equals to 1/4 of a period, which means that the coil will be like this, okay, vertical to the field, okay, we will have a flux of sine pi over 2, which is 1 times b times a. So we will have a maximum flux after 1/4 of a period, okay? So I'm going to write this down. Let me use a clean page. So if t is 0, flux is 0. If t is 1/4 of a period, phi is ba sine 2 pi t over 4 over t. So BA, which is phi max. All right. So E, the electromotive force, is d phi over dt. So this is equal to, this becomes equal to omega B A cos omega t. So if f, the frequency, doubles, omega, which is equal to 2 pi f, doubles. So E, the electromotive force, mth, doubles. And T, which is 1 over f, halves. Okay, so if we go back to this, we will see something like this. So if this was E naught, if we come up here and this is 2 E naught, okay, we will have something like this. This is half the period, I guess. So we'll have something like this. Oops. I'm so bad now. I'm so bad at this. So, okay, let me think. So it will be a maximum there and there. So it will be something like this. Anyway, for some reason I can't draw right now, but you get the idea. Okay, it's gonna be faster and stronger. Okay, let's move on. Okay. B. The magnetic flux density in the region between the magnets was 0.9 Tesla. By the way, you're not required to draw it anyway. I just tried, and for some reason I failed. Okay, let's try again. I became stubborn now. So, okay, you will have to start there, and you will have to end there, and let me see, in between there must be a 0. So one full oscillation, so something like this. Yes, okay, now I made it. And then it will continue like that. All right, so now B. The magnetic flux density in the region between the magnets was 0.9 Teslas. The teacher rotated the coil with a constant angular velocity omega equal to 1.57 radians per second. The maximum induced E max is given by the formula phi omega, where phi is the maximum flux linked with the coil. Calculate E max. They give you the width of the coil and the length of the coil. So E max is, okay, phi, the flux is B times A times omega, and then we have B times width times length times omega. So we simply plug in 0.9 times the width, 9.5 times 10 to the negative 2 times 12 times 10 to the negative 2 because it's meters, and then 1.57. And if you carry the calculation, the answer is, let me check my notes, 0.016 volts. Okay. And C, explain how Lenz's law applies to the motion of the coil. So the induced EMF, okay, will be such that, okay, a current flows through the loop, okay, that creates a magnetic field so as, this is an S, I'm sorry, so as to oppose the reason that created it. Okay, so a force opposing the movement is created. And for those of you who are watching for the first time, I'm sorry about my handwriting. I do my best, but sometimes it slips my attention and gets really bad. So, question 18. An inkjet printer produces tiny drops of ink called droplets. As the droplets are produced, they gain positive charge. Each ink droplet can be considered to be a positive point charge. The diagram represents a positive point charge. This is question A. Draw field lines to show the electric field around the point charge. Okay, so that's these are the electric field lines. Okay, you have to point outwards and be equally spaced, so something like that. Okay, B. The charged droplets pass through the uniform electric field between two metal plates and are deflected as shown. The potential difference across the metal plates is 45 volts, and the distance between the metal plates is 3 times 10 to the negative 4 meters. An ink droplet is between the plates for a time of 8.6 times 10 to the negative 5 seconds. The charge on the ink droplet is 1.4 times 10 to the negative 10 coulombs, and the mass of the ink droplet is 2.9 times 10 to the negative 10 kilograms. I. Calculate the vertical component of the velocity of the ink droplet just after it leaves the plates. Ignore gravitational forces. Okay, it sounds scarier than it actually is, but in the vertical direction, if we come here, okay, take droplet, the only thing there is the electric field, which points this way, right? So the only thing accelerating the droplet is the electric field, okay? So sum of all forces, actually let me specify that this is the vertical direction, okay? The sum of all forces is equal to the mass of the droplet times the acceleration in the vertical direction of the droplet. So what's the total force? Charge times the electric field is equal to m times AV, the vertical acceleration. So AV is Q times V over the mass of the droplet times D, where we use that the fact that for parallel plates, the electric field is equal to the voltage over the distance between the plates. So, okay, Q is 1.4 times 10 to the negative 10 coulombs. The voltage is 45, right? The mass of the droplet is 2.9 times 10 to the negative 10. This cancel. And then D is 3 times 10 to the negative 4 meters. And the acceleration we find is enormous, is 72,413.8 meters per second squared. And then we have to use Suvat equations in the vertical direction. So the final velocity in the vertical direction is equal to the initial velocity in the vertical direction plus the acceleration in the vertical direction times the time spent. The initial velocity in the vertical direction is 0. How do we know that? Because down here, as you can see, it doesn't really move up. It starts with only having horizontal velocity. Okay. So if we plug in numbers, 72,413.8 times 8.6 times 10 to the negative 5. So the vertical velocity is 6.23 meters per second. All right. Part 2. The horizontal component of the velocity of the ink droplet is 15.2 meters per second. The ink droplet collides with the paper and comes to rest. The maximum horizontal impulse needed for the ink droplet to stick to the paper is 4.2 times 10 to the negative 9 newtons times seconds. Deduce whether the horizontal impulse on the paper will be enough for the ink droplet to stick to the paper. All right, so the impulse is equal to delta P, right? So in this case, delta P is going to be the mass of the droplet times delta V. Okay, so assuming it stops, delta V is just the horizontal velocity. So we're going to have m of the droplet times V horizontal. So let's plug in numbers. 15.2 meters per second is the velocity times the mass of the droplet, 2.9 times 10 to the negative 10. This yields 4.41 times 10 to the negative 9 newtons times seconds, which is larger than 4.2 times 10 to the negative 9 newtons per second. So yes, all right, and a smile face. All right, 19. In the Bohr model of a hydrogen atom, an electron moves in a circular orbit around a proton. Okay. A particle orbits at point O in a circular path of radius r as shown. The particle moves at a constant speed v. The dots represent two positions, an angle theta apart. The acceleration of the particle is a. Derive the equation a equals v squared over r. Okay, so the way to do this is to denote this as vb. Okay, and okay, let's call this point A and point B pretty much. A and oops and B. Okay, so if we parallel transport the vectors, I will have VB. Okay, so that's VB, and then VA is going to be this vector, right? So that's VA. So I haven't done anything. I'm just taking this situation, I'm taking these vectors, and I move them down there, okay? All right. So, but delta V is VB minus VA, okay, vector-wise. So how do we subtract vectors? We add the opposite. So that's equal to VB plus minus VA. What's minus VA? It's this vector pointing this way. Okay, so that's minus VA. So how do we add them? We just connect the start of VB with the end of V of minus VA. So that's our delta V pretty much. So that's delta V. Okay. And the angle between these two vectors is theta. How do I know this? Because VB is perpendicular to the radius and VA is perpendicular to the radius. So that's VA and that's VB, by the way. And they both have the same magnitude. Okay, so notice that this triangle is similar to the triangle that the radii make between them. So the radii, for the radii, we have the first radius, and then we have the second radius r. This angle is theta, and this is delta r, right? So we have two similar triangles, okay? And for similar triangles, the ratio of corresponding sides are equal. So delta v over delta r, right? This is delta r and this is delta v, okay? So delta v over delta r is equal to v over r. So delta v is v over r delta r. And if we divide by time, delta v over delta t is v over r delta r over delta t. What is delta v over delta t? A. What is delta r over delta t? V. So A is v squared over r. And that's the proof. All right. This was kind of involved. B. The diagram below shows the Bohr model of a hydrogen atom. In the Bohr model, the electron orbits at a distance of 5.3 times 10 to the negative 11 meters from the proton. The electron has kinetic energy due to its motion and potential energy due to its electrostatic attraction to the proton. Determine the kinetic energy of the electron as predicted by the Bohr model. Okay, we need the kinetic energy of the electron. So this is the electron. How does it go around in a circular orbit? This is its velocity, and there must be, since it's a circular orbit, there must be a centripetal force that is perpendicular to this velocity. Okay, so the sum of all forces should be equal to mv squared over r. And what is this force? It's the Coulomb force. K. E is the charge of the proton times E is the charge of the electron. So E squared over R squared is equal to V squared over R. So these R cancels. And we need the kinetic energy. So we can multiply by 1/2. So 1/2 K E squared over R is equal to 1/2 mv squared. So that's the kinetic energy, right? So Ke is 1/2 times K, which is 8.99 times 10 to the 9. And then E is 1.6 times 10 to the negative 19 squared. And then R is what they give us, 5.3 times 10 to the negative 11. And if you carry the calculation, you will find 2.17 times 10 to the negative 18 joules. And if we divide by 1.6 times 10 to the negative 19, we can convert to electron volts, and we find 13.56 electron volts. This is one of the most popular results in quantum mechanics. Those of you who are going to go study physics at the university level, as well as engineers, electrical engineers, people who deal with electronics, stuff like that, people who take at least one lesson of advanced physics, modern physics, quantum mechanics, something like that, they will learn that. Okay, so let's move on. Part 2. Determine the potential energy of the electron as predicted by the Bohr model. Okay, so the potential energy is Q times the electric potential. What's the electric potential? And what's the charge? The charge is just minus E. I don't know if you need to use the minus sign. Let me check the mark scheme real quick. Curious. What did they do? Okay. By the way, our earlier result is correct. Yeah, they don't need the minus sign, but okay, it's minus because we know the electron has a negative charge. And then the potential is K E over R. This is the potential due to the proton in the center. Okay, so this is minus K E squared over R. So let's plug in numbers. Minus 8.99 times 10 to the 9 times 1.6 times 10 to the negative 19 squared over 5.3 times 10 to the negative 11 yields minus 4.3 times 10 to the negative 18 joules. And if we divide by 1.6 times 10 to the negative 19, we will find minus 27.14 electron volts. Okay, in the mark scheme, they say plus 27.14 electron volts. That's fine, I guess. So what is a minus sign among friends? Used to say one of my graduate school physics professors. So, okay. C. Question C. Suggest what will happen if an electron radiated energy when in orbit around a proton. If an electron starts radiating energy, it means that it loses energy, so it moves to a lower orbit or it spirals inwards. So Ke will decrease. Okay, and then the electron will spiral into the nucleus. All right, and this was Unit 4 from this January 2026. Again, there is a Unit 4A for January 2026. I plan to go over that too, but guys, I have other stuff going on as well, so I try to find times to make time for these videos. I'm really happy the channel started growing, but again, I mean, it's light years before I can monetize or make any significant, I don't know, living from this. But okay, so far so good, I guess. I plan to make more videos soon. Let me know what you think in the comments. Please like these videos, please subscribe, and yes, as I said, I plan to also do Edexcel papers from the UK curriculum as well as GCE papers. But we'll see. I mean, I don't have infinite time in my hands. So see you in the next video, guys. Bye.